Hi everyone. Let's get started. We have a full plate today, literally and not literally. So, just to put us in context in terms of a timeline, today is the next to last lecture that I'll be giving. So next week is the last lecture. Today is also we're giving out the last exercise. So when you go through the last exercise, last effort on doing that, within the last exercise, you'll also find the instructions for the final project, as well as the allocation of the date and time of your presentation. If something doesn't work, doesn't fit, you can talk with the teaching fellows and see what we could do about it. Okay? So it's all coming up. The week after the last exercise, after the next lesson, you'll have time off to keep on. We want to give those who are the first to present to have more time to present. You'll see in the instructions we have a pretty cool method. You'll have a mentor from the class that would help you with that. So there's a whole preparation format, which we think is important so that you use the time most efficiently, both for you and for all of your lively audience. Good. So let's jump into the session today, and I'd like to start with a concrete question. What is the maximal height you can climb with the energy from a snack bar? So you already know I'm giving you very concrete questions because we think this is a good way to learn. Along the way, we learn things about food, about energy, etc. But the underlying hidden agenda is to show to you that A, doing quantitative reasoning is useful. You learn interesting things about the world. And B, it's not rocket science, it's our science. Like it's a sort of proficiency that, requires multiplying and dividing, something we know pretty well, and having a good quantitative numerical logic, which I think you already have or you can improve during class. Okay, so think for a second about this question and how would you try to approach it. So, the first thing we try to do with such a question, we try to find some way of do some sort of divide and conquer. Yes.
I think it's with the energy equilibrium you can solve this. You say if the potential energy you have, you can calculate m times g times the height. Let's say like the maximum height you can think of, and the energy from the snack bar is like the calories of the chocolate, and those have to be even, assumed at the maximum heights you reach by it, and then you transfer the equation to h, like the height.
Fantastic. So out of all the problems that we've been doing in class, I think this is the first one, maybe only one ever, that also has a bit of physics. But we wouldn't push you too far. So the suggestion here is to look at, I want to climb a mountain. And now I'll start the path here, and I'll walk up to some height. And now saying, okay, the question is, how much is this maximal elevation I could walk through, right? And we're saying, for that, I'll be eating a snack bar. Black snack bar, not very popular.
Chocolate, dark chocolate.
Dark chocolate, good. And so we want to make this energy equal to that energy, right? Okay, how much is this energy? So you're saying it depends on the elevation. So that's a delta H of how much we would go up. And then there's this thing, I hope you remember it. If not, I'm helping you. It's the mass of the person times G, the constant of gravity, and H. This would be the energy associated. On the other hand, we have the snack bar. What about the snack bar? The snack bar also has a mass and times the caloric density. And we'd like to make these two equal. That's the idea. Yeah.
Could someone try and go about it in a different way by trying to calculate the energy per step taken, and then the calories of the snack bar.
Maybe.
That way.
Yeah, so that's an alternative way to do it. In such things where you have more than one way, I often am curious, or like, first of all, it's good to do both and see, but it's interesting to try and look for something that would be as robust as possible. Meaning, let's say we'll have to have several things here that we need to know, like what?
Average mass.
So we'll need to know, say, the mass of the person, we need to know the mass of the snack bar, so there's things like that. But, and I think we could make reasonable estimates on that. Then in the method that you just suggested, we have to know what's the, like how much energy do you need in order to make a step. That's a tougher one, I would say. And also, how much are you climbing in that step? That's also not so easy. Anyway, so this is just like reasons to think about, when you're doing such comparisons. Yeah.
But you can like see like chart of like how much energy do you burn in some sort of exercise, and you can use that, and it will be significantly different between the height, like with the potential energy, because the body is burning a lot of calorie just to exist.
Okay, so the point that you raise is that this is a calculation on the maximal height, in theory, that you can climb based on this, the potential energy, etc. And you're saying in practice, it might be different because of physiological constraints, conversion energy, etc. Very valid. We could get to it. That would answer a different question, not the maximal theoretical one, but more like kind of like a practical one. So we could also look, reflect on that in a minute. Okay, we could continue giving all sorts of comments, but let's do some work and then we go back to other insights on this. Okay, so let's try and look at that. So what's the weight of a snack bar? Anybody's
Why is it important?
what?
100 grams.
Why is it important?
Why is it important?
Yeah, because I know that the calories is the main thing.
Okay, so you could say if you know maybe the total calories in snack bar. This would be equal to this. Yeah, so if you know the total number of calories in a snack bar, you can do that. But I kind of like this because this gives me a more fundamental thing, because once I know caloric density, I can know the caloric content of everything in the world. Whereas if I know just for calorie in snack bar, maybe it's good for my, how I, like it's good for that, but not good for many, many other things. Okay, so that's but you know how many you have in your?
150?
150. Okay.
If it's the identical one.
Okay, so it probably depends on the snack bar, but okay. So
500 per 100 gram. No, most of this chocolate and all these sweets has like around 500 per 100 gram.
okay, so we have so let's try to approach it this way. We could do it in two independent ways. There's somebody who knows, the calories and things they eat, and say roughly 200 kilocalories. Okay? Notice, by the way, that I wrote it this way. I did not write it in the way you write it very often in your exercises, as this way. Why?
We can see what that means proportional too, right? This sign? No?
So I'm saying I didn't write it as double. I wrote it as double tilde, not as single tilde. Single tilde is much easier, nicer to do on the keyboard, because just like shift something. If you want to do double tilde, I know on my Mac it's also just Alt or Shift X, so it's not such a big deal. But in Word you have to find it and symbol, blah blah blah. But still, I insist that I very much prefer this over this. Anybody knows why? Except for somebody who already said it.
It's a different meaning.
It has a different meaning. What's the different meaning?
The upper one is approximate, and the lower one is like
Yeah, so this means approximately equal. Whereas this one means proportional. Or it has more than mathematical. This is either proportional or order of magnitude. Okay, so I'm a bit anal about this, I know. So, it's not such a big deal and many people don't care about this, but, given that you're in this course, I could, teach you also that. This kind of like means this is the order of magnitude. So that's kind of like it's somewhere between 100 and 1000. Okay? Which, again, it's the right order of magnitude. But I think, anyway, and if somebody's going on a diet, I think they care a lot if it's 100 or 1000. Right? It means like whether you can eat something else today or not. Okay? So it's a big deal. It's like saying, like in terms of what the diet would do to you, either you lose, 1 kilogram or 10 kilograms. It's a big deal these days, or 5 kilograms and 50 kilograms. So order of magnitude is good for many things, but for other things where you really know, say within twofold or something like that, when I'm saying 200 here, I'm saying it's somewhere between, 100 and 300. Okay, much, much tighter uncertainty. And then the right mathematical symbol for that is the double tilde, which means approximately equal. Okay, there was a comment question.
So there is the equal sign and the tilde above it. Is it
Yeah, so there's, don't do it.
Okay.
Don't do it.
It's easier to do also in words. So.
Yeah. So that has a different meaning depending on, in geometry it means one thing, and this means some other thing. So I recommend this. Also, it gives you like you have a personal style. Anyway. Okay, good. So we're done with that. So that's, okay, this was one thing. Okay, but we were here. Okay, yeah?
maybe we should add the calories to mechanical energy transfer efficiency.
Maybe we'll get to that if we need. Okay, so we said about the weight of the snack bar.
50 grams, 80 grams.
30.
Okay, so something like 50 grams. What do we know about caloric density?
If it's sugar, it's around 400 kilocalories per 100 grams.
Okay, anybody know some more?
It's fat, it's double.
Okay, if it's fat, it's?
Double.
Okay, so that's kind of like what usually people need to know in order to make lots of inferences. So this, what was Eviatar was stating is that you have 400 kilocalories per 100 gram. This is sugar.
It's also true for protein.
What?
It's also true for protein.
Right. So yeah. So let me write it differently. Sorry. So this value of 4 kilocalories per gram, that's true for sugar, for protein. Anything else?
Carbohydrates in general.
Actually, carbohydrates in general, all carbohydrates. So this is pretty useful. And what is the other thing that we're eating that has caloric intake, caloric density? Yeah, so fat. And fat has a different rule of thumb. That's about 9 kilocalories per gram. This is what? Fat. Fat, oil, right? Butter as an example. Good. So if I know this, so I have some mix here between this and that. Depends on what kind of snack bar you're having. But you see that this is going to fit pretty well if I'm taking just, you say most of it is carbohydrates. So this is 4 kilocalories per gram. Maybe it would be 5 here. Yeah? So this gives you also the same value that was known here, 200 kilocalories per gram. Okay, per snack bar. how much can I climb? So, what's the mass of our person?
70.
Could be 70. I want to make it round, so I'll just put it as 100 just to have it easy to make the calculations. How much is G?
10.
9.8.
10. We would have the units here, which I think meter per second square. Okay, and now we're gonna derive the height. But I have a bit of a small problem here, which is what?
Units.
Something with the unit is problematic, right? Because I have here the value is 200, it's kilo, so it's 200 times 10 to the 3 calories. And calories are these funny units, they're not in the metric system, so they could not be dealt with this.
It's like 4
Yeah.
joules.
I think 1 kilogram times meter divided by second to the square is the same as 1 Newton in terms of units. Does it help us? Yes, because 1 Newton is like joule times meter.
That's all true, but there was somebody who was saying something, yeah.
It's a calorie is about 4 joules, and then
Yeah.
you can go through the same conversion.
Right, so a calorie, so the way I'm doing it, I want to multiply, I want to say 1 calorie, and I want to have something here in units of joule. Joule is the energy in the metric system, and that's roughly 4. I think 4.2 or something like that. Anybody knows why? How did we come up with all this stuff? Of like why use calories, etc.?
It's to heat water, like to heat 1 milliliter of water 1 degree Celsius.
Exactly. So say 1 milliliter or 1 gram of water. With 1 calorie, you can increase its temperature by 1 degree Celsius. So it's also a nice way to talk about energy, more like a thermal energy. Nice. So what do we have here? We're getting about 800,000 joules. And this should be equal to, we have 1,000 times the height. So from this we get the height being 1,000 and 1,000. The height is, okay, this also has units. I'm not being very nice in terms of units. So this is kilogram meter per second square times the height. And from that you can see that the height is going to be 800 meters.
But what about the angle? It's just the height. Is it going to climb its face wall?
Okay, nice. So this was, what about the angle? Okay, so what's the answer? We were calculating here something like, an ideal maximal height, just in terms of the total energy. And now you could say, hey, actually, when I was climbing, I don't know, some serious height, usually you don't climb 800, you climb, say, 400, 300, and you definitely want to have a snack bar in terms of how you feel exhausted. So this is like kind of like a theoretical of how much if everything worked perfectly. There's at least 2 things here. One is you were talking about the fact that, I'll also be walking, in some other thing, which is some exertion, but in general, the efficiency of conversion is not 100%. Okay? How much is it? It depends. But let's say very often conversions of things in our body, they're like about few tens of percents. Okay, somewhere between 1/4 and 1/2. Okay, so that means that instead of 800 meters, I would say, effectively for every 300 meters or so, few hundred meters that you're going up, that's the amount of energy that you would need. Good, so what did we have here? I think there's something for me kind of like rewarding in the fact that I could ask a question that's very, large scale, on the scale of a person, and also connect that to something like a snack bar, which is also that. And in order to solve that, I could go and use just numbers that I know about, density of food and things like that. I think there's this interesting connection. But you might be troubled by the fact that, this, you needed to know, right? Like we didn't infer them from basic principles. So first of all, I'll say there is a way to infer them, but this requires more time and a bit more of a play around with physics and electrovolts and energies on the microscopic scale, and I'm not sure we have the time and patience for that. But I would say on this, it's pretty useful. Like if you care about, your health or doing all sorts of calculations about food, about physiology, etc., this comes out pretty handy just to know these things about the things that we're eating. But I'm still curious about the fact of, so all of these things, let's say, this is the sort of thing you make bread from. Bread is mostly carbohydrates. And let's say this, I'm taking the example of butter, and I could ask why does butter have much higher caloric density than bread? I don't know if you ever asked yourself this, but in general you could ask, okay, why does oil much higher density than sugar? And I want to try to approach it in order to show you now a connection between how, also these kind of questions, how you can try and find simple quantitative arguments to make sense with things. And it's interesting because I was asking that, just before this lecture, I was talking about it with a colleague of mine who's actually dealing a lot with, with food and sustainability and agriculture, etc. And he was telling me, this question, it's very complicated because, sugars or, carbohydrates, they come in so many different varieties. It could be like a small one, like glucose, or it could be all sorts of, starch or things that are really long. So it could be like a huge polymer. So it could vary by orders of magnitude in terms of what you have there. And similarly, in terms of oils, you have many different types of oils and fats, etc. So I'm curious. So even him, he's a super smart guy. So it is a complicated problem, and I try to see if I can get to the heart of it to try and find an easy way to understand things. Yeah.
Maybe the ratio between reduced carbon and oxidized carbon. That's how we produce energy in cell. We actually oxidize carbon, so if you have more of it in a gram, you have more energy.
Okay, so I don't know if everybody follows the biochemical argument, but let me try to repeat that. What Eviatar is saying, maybe it's something about how reduced or oxidized the carbon is. So both of them are carbon-based. So let's just remind ourselves some stuff. What are we talking about when we talk about this? If it's a sugar, how does it look in terms of... Yeah, so it could be like, say, C6, H12, O6, or things of that sort, let's say for glucose. And if we're talking about, say, a lipid, oil, fat, what's happening there? So people are doing like this. So these are like carbons, and on each carbon you have 2 hydrogens. That's about right. Mm-hmm. That's also as far as my biochemistry goes. So I'm happy we don't have to push much further than that. So what do we do with that? Okay, so you're saying this one in terms of reduction, it has these 2 hydrogen. This one in terms of reduction, all of those oxygens, and therefore it oxidizes it, and that's part of it. Good. So after I had this discussion with my colleague, I told him what I'm going to tell you. I told him, no. It's much more, it's different and this and that. And so we had to And there was a question of how do you even know those numbers? How do you know those numbers?
You burn it.
You just don't tell us. Calorimeter.
Yeah, so you're doing calorimetry, so basically you're burning it. But when we were discussing, is this the way you do it? So I told him, yeah, that's I think it is, but he wasn't sure because there's, in terms of our physiology, maybe you need to convert it to how many ATPs you can get out of it and all that. So I went to check. So how did I check it? I went to ChatGPT. I chose, the best, mode of thinking, 5 point something. We pay for it a lot of money, but it's really cool. And, I got the answer that indeed it's based on the caloric, it's called bomb calorimetry, which is a very nice name. It's like a bomb calorimetry. And indeed it is about heating. It's not about how many ATPs you make. But it was really nice because, Igdil Rosh, like ChatGPT is really thinking, trying to help me. So it also explained to me why is it so, which I think it's also because he knows already that I always want to get back of the envelope calculation, things like that. So he did like a nice thing about it. And he explained exactly like the sort of, so actually it didn't go exactly like that. He started, the first thing he said, that the difference is because of the hydrogen to carbon ratio. So it's a different carbon to hydrogen ratio, which I was really, I think I would have been really satisfied with that and could continue. But then I looked a bit more different. I said the carbon to hydrogen ratio, for every carbon I have 2 hydrogen. And here for every carbon I have 2 hydrogen. So what is it, Chet? What do you want from me? Why is the carbon to hydrogen? No, I apologize. It really is, you're very absolutely right. Very perceptive of you. It's not about the carbon to hydrogen ratio. It's about the oxidation state of carbon. Okay, which is what you said. The problem is, I think it's something else. So let me show you what I got, and then we could go back to my discussion with ChatGPT. Okay, but I would say it was very persuasive. How he wrote it, I'll be, if I didn't need to teach it and thought about it for many years, I probably would have just said, yeah, no problem. Okay, so why is it different? Let's look this and the fact that it actually hides, like you can try and simplify and go at the heart of things. Okay, what's the heart of things? If you look at how does a sugar, carbohydrate, etc. looks, you have a carbon, it has a hydrogen, it has an oxygen and hydrogen, and then here you have more repeating units. So you can write it this way. It's like n times. Okay, in this case it's 6 times. Make sense? Okay, it's like a chain with repeating units. Maybe they close at some point, maybe they branch at some point, but it's basically this. Okay, what about this guy? This guy is also kind of similar. It's a carbon, hydrogen, another hydrogen, and then it connects to its friends. So it's also a chain. Very similar. Only difference between a hydrocarbon and the carbohydrate is the oxygen there. Okay, now when I do, when I eat it or when I burn it or whatever, there's all sorts of bonds being broken, bonds being created, etc. But you know what? Let's just look, whatever energy comes out in each thing when you burn it, in terms of density, there's an interesting thing happening here because let's say I'm getting the same energy from both. I don't want to get into all the details of the bonding and the quantum mechanics of everything that happens here. Whatever energy I have, in terms of the energy density, I have to divide how much energy I get per weight, right? It's all per gram. Okay? So let's calculate what's the molecular weight of each one. What's the molecular weight of this repeating unit?
14.
So I need to know the weight of a carbon. So I'm molecular weight of a lipid. So it's 12 plus 2 times 1, 14. 14 Dalton. Okay, the 2 hydrogen and the carbon. Good. What about this one?
It's more.
I have the 12. I have the 2 times 1. And I have another 16, which comes from the oxygen. So this is 30 Dalton. So you can see per unit, per repeating unit, this weighs twice as much as this, a bit more than twice. Somebody sees like an interesting coincidence here.
Yeah, okay.
So the density is also about 2 to 1. So basically the repeating unit is twice lighter here, and the density then becomes twice higher. Okay, so that's a very easy way to see what's happening here, at least the major effect.
But it's the opposite.
Yeah, if it's lighter, it seems like we would need to count more.
Okay, so the comment here is that this is in the opposite direction. Is it in the opposite direction? Okay, it might say, so this is confusing. Always things, whether they're opposite or not, could be confusing. So let's see. The thing that we're talking about, this one, the fat, oil, etc., they have this structure, this repeating unit, which is the light one. So if you have something that gives you the same amount of energy, but it's light, the density would be higher, which is what we're getting. Okay, you could keep on thinking about yeah.
No, I was just wondering if that matters, that if this data, like all this energy data is based on how much energy you need to heat it with the calorimeter approach, is it not like that in fatty acids there's like a lot of overlap between the molecules, so you need to invest more energy, like to separate them kind of, or something like this? Or is that something we can neglect?
I think
Like the intermolecular energy.
yeah, I think we could happily neglect it. But I think this also shows this sort of thing that can often confuse us. That there's many different other points, but the question is whether quantitatively they're dominant or not. So I think that issue is kind of negligible.
So usually fats have free fatty acids and glycerol, so it's not even a single unit repeating.
Right. So you can go into. So it's true that you have a chain here. At the end of the chain, maybe you have like a carboxylic group or something like that, and then you can try and include that.
No, but not the curves. On the other side, you have glycerol, and then you have three fatty acids going next to the other.
Yeah. Yes. So you could take that. You could look how much does that add. Actually, I think this is like a second order effect, which, by the way, I think kind of like cancel. So you also had a good comment that in terms of the reduction state, it's different. So that adds another effect, which I think about cancels the effect of what they have at the end of those chains. So this also goes to the fact that, there are, say, what ChatGPT was trying to push for is another way to explain it, which is not completely wrong after I corrected the first thing, which was wrong, but it's actually not the major quantitative aspect. It's an extra bit of information. Okay, yeah.
The first thing that ChatGPT said wasn't completely wrong. Because if you're talking about hydrogen to carbon ratios inside of like fat acid, it gives you how much it's saturated. And it also shows you about the oxidation state of the chain.
Okay, so there is an issue about the oil, the fatty acids, how saturated or unsaturated they are, and that could vary somewhat. I would say that's also true, and also like a second order effect, much smaller. So in the big picture, to explain this and that, this gives the molecular weight, governs the density, gives us a good, the most of the explanation. Let's say 80% of the explanation. Now there's another 20% that could be related to all sorts of things, and sometimes they're in the right side, maybe the reverse, etc. Okay, so just to wrap things up, so we calculated how maximal height you can get to. We take into account this is not perfect, you can get somewhat less. And in terms of understanding the molecular things we had to go through, there's actually a way to think about it and to get those values. Good. Yeah.
So we were just discussing it. Is it not the bond between the energies maybe the thing that can really help us? It's then like the energy value of the atomic bond.
Yeah. So all of this you could also have derived by doing the complete simulation of the bond breaking and bond formation with all of these complicated thermodynamics, etc. And it could have created maybe some extra effect. What I'm showing here is that basically, even without knowing all of those detailed transformations, etc., I can really get roughly the ratio of things just from understanding things that are quite simple to derive and understand. Nice. So we did that. Before we take a break, I want to give you a challenge. And that is, what is the power of a human being? What do I mean by that? What is this power that I have in mind? Yeah, so I'm talking, I'm in a lecture that thinks about, things like energy, etc. And then power is, a well-defined thing, which is what?
What?
Okay, so watt is the unit, but that power is energy consumption per unit time. Could be energy consumption, energy production, which is usually equal because we're like in some sort of a steady state. And so my challenge to you for the 10 minutes recess is to try and see if you can estimate that.
So if I estimate the calories for all day.
So yeah, well, find out so maybe we'll start with like 2 minutes of each person before we head out. Try to see either by yourself or in pairs to try and see if you can get to a value. In the end, I want like a number.
Which unit of time?
Okay, which unit? So let's talk about units. So maybe let's just enjoy ourselves. Let's just throw all sorts of units that you are aware of that relates to these things. What units do we? Okay, so I've heard joules. What else? Calories. Again?
Kilocalories?
Kilocalories.
Joule per second.
Let's just take units, not units divided by units. Other units?
Days.
Days. Okay, days is unit of time. I'm looking for something that relates to energy. I had watt. Anything else? Any more units you know about? Horsepower, good. Okay, there's things like BTU, there's, barrels of oil. There's all sorts of, it's a subject where it explodes with different units. Kilowatt hour. There's actually a ton of TNT. Okay, so the important thing to know about this is there's a difference between these and these. Okay, these are units of energy.
Without time.
These and there's others are units of power, which is energy divided by time. Okay, and the key numbers are, say, joule and watts. The conversion between them is that 1 watt is 1 joule per second. Okay, so now you know everything you need to know. Try to tell me how much energy drives you, or how much energy you consume.
It's the last.
So let's wait here. I want to see that we're making some progress together, and then we head out.
כן, 4.5.
טוב, חבל שלא שאלת. כן, אז הכל עשיתי ב-dry mass. הכל כאילו על מסה יבשה. זה כמעט לא, זה קטן מאוד, אבל זה נכון שהכל האחים היו על dry mass. זה באמת אני צריך... מה? כן, אפילו זה יוצא אבל בסוף אותו דבר, כאילו יוצא מאוד קרוב, אבל זה באמת כבר קשה to derive it. Okay, let's take a 10 minutes break. You can keep on discussing if you want, and we'll reconvene here. Okay, so can somebody help me know how much power I have? Yeah. How do we do it? So how do we approach the question?
How many calories do you take a day?
Okay, how many calories?
2,000 kilocalories.
So I have calories per day, and from that I can convert to power. Okay, so 2,000 kilocalories per day. What's your favorite way to convert it from here?
Calories to joules, day to
Okay, so there's several ways to do it. One way is to say, okay, this is 2,000, but I can say, yeah.
8,000 joules.
So I can go to the joules. Good. Let me just try to do it in a few other funny ways to do it. So 2,000 is about 20 hours a day. So this is about 100 kilocalories per hour. Which, as an aside, I'll just say, if a person weighs 100 kilograms, that means this is also equal to 1 kilocalorie per kilogram per hour, which is just like a nice, cool value to carry in your head. For every kilogram in your body, every hour you need to supply it with 1 kilocalorie. Okay, but forget about this. It's just like a fun fact along the way. Now you can, if you want, you can do the conversion from, you have 1 kilocalorie, it's 4,000 joules, okay? Because of the K, it's the 1,000. Because of the calorie, it's the extra factor of 4. And if you're really interested, you also want to get rid of the hour, because in the end we need to go to seconds. Okay, so I do the same trick. I want to do multiply by 1. This was 1. This would be another 1. 1 hour, how many seconds? 3,600. And 3,600 and 4,000 is roughly the same. So I get 100. I'm just left with this. And now, let me enjoy myself. The kilocalories falls with the kilocalories. The hours falls with the hours. And I'm just left with joule per second. So 100 watts. Okay, obviously it has to be, it should be like, this is equal, but somewhere here I needed to say roughly. Okay, yeah.
Just for fun, we also calculated it in moles of ATP per second, and we got 1/300th of a mole of ATP per second.
Okay. So we have that, and now let's move from here, given that now you know how much energy you need to fuel yourself. Let's go from here to the natural follow-up question. which is what? So you might remember that last time, in an exercise, you had to go to this nice effort of anthropo numbers, looking at all sorts of numbers related to the impact of humanity. And one thing that we heard from many people that were interesting for them there, or surprising for them, is what is the land required to feed one person on average.
Carnivore?
What?
Carnivore?
So the question is, globally, how much land do you need in order to grow your food? Okay? Anybody remembers what was what?
Football field per person.
Yeah, so I think some people wrote to us that they were quite taken aback by the fact that it was, I think it was like one soccer field per person. Okay? And it rubbed them, it didn't make so much sense necessarily because a soccer field, I guess, pretty big. Does every person need that much?
For how long? To feed for how
Okay, great question. For how long?
1 year.
No, it's year round. It's constantly.
You grow
Same land. The land doesn't change. It
No,
grows
but how
crops.
much-
You recycle.
To sustain you
For 1 year?
constantly. No,
Ah.
constantly.
Lifetime.
Okay, so the question is that soccer field, or whatever the answer would be, over how long? So it's kind of confusing. It's not, because I think the question is rightly posed because you need some food per unit time. The thing is that also a land also gives you some food per unit time. Okay? So if I have the person and the field, both of them give you, this as a requirement per unit time and this as a supply per unit time. So in the end, the result is independent of time because the two things cancel out. Now it's true that, like, say, if you have a field here, usually it would give something once a year or twice a year, depends how many rotations. So you can't come on a random day and eat what's on the field. So it's kind of like, you can think it's like a yearly average. Like you take all the potatoes that came out of the field, you store them, and then every day you eat one potato, and then it's smoothed out over the year. Okay, but in the end, this does not require, it's not land per unit time, but it's like, land on average would need. Good. So how do we check if this value of soccer field makes sense or not? I want to try and see if we can make again, try to perform sort of a sanity check based on other things that I might know or not know. So let me suggest how to try and divide and conquer this problem. I know how to do two schematics, a person, and what's the other one? Earth. Good, so I want to see on this earth how much land do I have that grows food and how many people consume the food. So what do we know about the earth? 70% is water, so I don't grow food on you can grow some, but this is not how we make most of our food. So it's mostly land-based. How much is the land surface area? Anybody remembers?
The land is 150.
Right, so we already did it several times, so I'm just jumping directly. It's 150 million kilometers squared. Okay? Out of that, I'm asking myself how much goes into agriculture, all of agriculture in its different forms and shapes. Anybody have a gut feeling?
Half.
50%.
2/3.
Okay, so we had 10% and we had 50, that was the lowest, 50 to 2/3 the highest. So I would go to the original answer of 1/3, which is also roughly the correct answer. That's about 1/3 of the land goes into agriculture. So that means that altogether I have about 50 million kilometers squared. How many people I have to feed with this on Earth? So about 10 billion, but just for the fun of it for now, let's make it, the real value, which is about 8 billion people. In a minute, I'll show you why I care about this, putting it as 8. So how much is that in terms of how much area I need? So maybe it would be useful to get rid of the kilometers because we're not used to think in kilometers squared about I don't know, small parcels of land. So as usual, I would have here 1 kilometer, 10 to the 3 meters, and all of this needs to be squared. So I have a factor of 10 to the 6. So I have 5 times 10 to the 6, 10 to the 12, another one, 10 to the 13, divided by 8 times 10 to the 9, right? This is meters squared per person. How much is this? 50. I'll take it as 50. 50 divided by 8. It's roughly 7. And this is now 10 to the 12, 10 to the 9. So I have 10 to the 3 meters squared. Okay, 7,000 meters squared. What's the area of a soccer field? Anybody knows?
7,000. What was written in the...
But how much is it? Somebody can Google it. I'm not playing soccer so much, so.
7,000.
Okay, no, yeah. So it's actually past the sanity check. Okay, this is roughly the area of a standard soccer field. Somebody had a comment along the way?
I think I was wrong. I thought agriculture is like the food for people like from vegetables or plants you grow, but what about like when you eat meat? But on the other hand, then Oshad said that you ought to grow vegetables, not to feed the animals, so it's kind of included.
Yeah,
right?
80% of cows, it's soy. So
Okay, so there's a question here about what happens here in terms of, so this is a lot of land, okay? Like a soccer field per person. And maybe to some of you it might also be surprising, like if you ask your grandma or grandfather, they used to be able to grow when it was still that families would grow much of their food on their plot. They usually didn't have a soccer field next to them or a few soccer fields if they were a family of a few people. Usually they could do with less than that. So something here is kind of like interesting, surprising in terms of that. And I think that connects to the comment here about the issue of food that goes into animals and how are we using animals. Because it turns out that this 1/3 of the land, the majority of it is actually not used to feed us directly. About 2/3 is what's known as pasture land. Okay, pasture land is where you send the cows, the sheep, the goats. Okay, so this is what gives you 1/3. If you only look at cropland, cropland is what you usually used to think about as agriculture, which is like where you really sow crops, etc. This is only 1/3 of the 1/3. Okay, so if you only take the cropland, instead of being 50 million, 1/3 of it is about 16 million kilometers squared. So if I take only 1/3 of that, 16 million kilometers squared with 8 billion people, I don't repeat the calculation, I'm getting roughly 2,000 meters squared per person. This is when I only took places where I form agriculture kind of like, in the more intensively with cropland.
And still 60%, I think, of that goes to feed.
Okay, so we could get in that. So not 60%, about 30%, something like that. So there is a non-negligible fraction, but say the majority of that. And we could talk about it in a minute. Okay, so this is like if you include pasture land. If not, this is the amount of land that you need per person. Also quite a lot, I would say. Yeah?
Should we go about it the other way around? Like try to calculate how much an average person eats and then to reason out that?
Yeah, so let's try and do that in a minute as well. Okay? So before we go and do that, I'm curious if this is what I'm using to, we're using as agriculture. I'm interested in the efficiency of this. Okay? What do I mean? I'm asking myself, what is the efficiency at which agriculture turns solar energy into the food we eat. And you know what? I think it's unfair to say agriculture because it's really the way we humans choose to run this stuff. We'll talk about it later, at which I could just do like this. What is the efficiency at which humanity feeds itself? Question is clear? We didn't do any vote for a long time, and we want to be able to keep that proficiency alive. We might need it. So is it about 10% or few percent or 1% or 0. few percent or I'm becoming tired, 0.1% or 0.0 few percent?
Can you define efficiency?
Yeah. The efficiency I define as how much solar energy is arriving on this 200 meter squared versus the energy that I'm consuming, which is how much?
100 watts.
100 watts. Okay, this is 2,000 kilocalories I'm eating. That's 100 watts. So I want to compare between the energy that's arriving, or the energy per unit time, and the energy per unit time that we're eating.
This assumption is a bit problematic because also the plant's efficiency is only 40% of photosynthesis.
I didn't ask. I was asking you a concrete question. I don't. This is a question, not another. Yeah.
About all the wavelengths or just the ones that are relevant to photosynthesis?
Same answer. This is like the question, what's the efficiency between the total energy that arrives in the solar radiation and the energy that is actually used in us feeding on that 2,000 square meter. Okay? You can resist the voting, but you have to vote.
Okay.
Okay, so who's voting for 10%? 1. Who's voting for few percent? Few. Who's voting for 1%? More people. Who's voting for 0. few%? Most so far. 0.1%, roughly the same. Who's voting for 0.0F? Another 3 people. Okay. I thought I'll give many options. We'll have, I can put more options and then there are more people voting. So we're all over the place. Okay, that's why it's good to be able to do a calculation. So we don't have to just form a coalition here and do things based on democracy. We do it based on the actual calculation. Okay, what is missing for us in order to be able to do the calculation? Yeah, the 100 watts we already know. Now we're only left with the energy of the sun. So what do we need to know? We need to know if we have a square meter. and we have the energy coming from the sun, how much energy would reach that, or what would be the power of the sun?
250 watts.
How much?
250.
250 watts.
Like the cloud.
So she asked, how do you know that it's 250 watts?
From the intro to climate class.
Because you came from another lecture where they talked about it. Okay, this is helpful if you took the class. What if you didn't take the class?
Google.
Yeah, so you can Google it and you'll find, so there's two ways to do it basically. Either like we could also estimate it. Let's just, before we Google just for a second, let's say I was asking you, I don't know if it's a good one. Yeah, I have like a square meter and try to think in light bulbs. Okay, how many light bulbs, say in order to give you the light and the warmth that you get from it, how many light bulbs, let's say incandescent light, like the ones you used to from the past that also give some warmth, etc., do you need in order to give you the same effect?
1,000.
1,000. Okay, so so I connect to the 10. Let's say if I'm per square meter, something like 10 light bulbs, and and if every light bulb is a few tens of watts or 100 watts or something like that, this gives me roughly what was stated here, something on the order of a few hundreds. Okay, this is just to give you like an intuition for that. But you can also Google it, and what you'll find is that it's known as the solar constant, I guess. So outside of the atmosphere, it's about 1,300. After you pass through the atmosphere, it's about 1,000. So it's 1,000 watts per square meter. Okay, so it's a nice round number. It's like 10 light bulbs, 100 watts each. Okay. Now this is when the sun hits it from, in the middle of the day, when it hits you, boom. But now we want to take this day and night, and there's the sunrise and sunset and the cosine of the degree and all of that stuff. I want to make it all simple. So I want to know if I have the Earth. These values, if I was looking at the cross section of all the sunlight reaching, it would have been this. But if I were to take the average over everything, you might remember we had a cool thing happening with that. Somebody remembers? Yes, exactly. So if I took the cross section, it would be pi r squared. Okay, because that's the area of a circle. And if I'm taking the surface area of a sphere, it's 4 pi r squared. So between this and that, there's a factor of 4 that takes into account, say, factor of 2 is from, this is the day, this is in night, so I'm losing about half. And there's all the cosines of the degrees, blah, 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 blah. It's another factor of 2. Very elegant, comes out to a factor of 4. So that means that instead of 1,000 watts, on average, I have about 250 watts, which, by amazing coincidence, is the number that was mentioned in the beginning from a different course. So even if you took the course just very shortened, okay? You get a pass on that course. Okay, so this is how much energy I'm getting in. Good. So let's use this. So 2,000 meters squared per person times 200 watts or 250. No, I can keep it with watts, sorry. So how much is that? What?
Watts per meter square.
Per meter square, yeah. Thanks. So this means that I have 500,000 watts per person. And I'm getting, for every person, 100. Let's write it here. 100 watts per person, that's eaten and this is supplied by the sun. So the efficiency is 100 divided by 500,000. That's about 0.02%. Who voted for F? Good job. What do you say?
We need to start doing photosynthesis.
I think this is shocking. I think this is shockingly low.
And there's still a food.
So basically, so this is 500 kilowatts. So if you think 500 kilowatts, like, every time you put like some, warming, like some things to warm you, it's about a kilowatt usually in terms of the electricity power demand. So you have 500 of these working. It's like, if we put it in the room here, it would heat up like crazy, super fast. There was a question, comment?
Oh, they said like that doesn't even include the amount that's wasted then once it's produced.
Okay, so now let's start to dig into this, about this number, what is whatever. But when I see such a thing, I want to make some sort of a sanity check to see if I got something wrong, because maybe something is wrong here. Yeah.
But it makes sense because all the energy that arrives to the land you mentioned is not totally converted to food. When you grow food, like plants, you eat only, I don't know, the fruit or part of it, and the plant uses, I guess, a lot more than you consume, like, as the end consumer.
Yeah, so you're right, we're not consuming everything there. Now the question is whether if you told me you're consuming 0.02%, for me it's shocking low. But maybe other people have other intuition. Wait a second. Okay, so I want to be able to do some sanity check on this. How would I approach that? I could say, all of this was like with these watts and, units, joules, etc. Maybe I'm confused somewhere. Let's try to do it in some independent manner. What's like an independent manner? I could ask myself, how much am I eating?
2,000 calories per day.
Okay, so we're back to 2,000 kilocalories per day. But these 2,000 kilocalories per day, let's say I want to work in units of weight. Like how much would that weigh?
So one kilocalories for 1 kilo, something like this.
So let's try to use what we just talked about. We passed, if I want to talk about, the things that I'm eating, what am I mostly eating? Most of our calories coming from?
Sugar and carbohydrates.
Usually they're things like sugar, carbohydrates, the vast majority. What's the density of carbohydrates in terms of calories?
4.
So if I have 2,000 kilocalories that a person eats, and the density is 4 kilocalories per gram. Notice, by the way, all these numbers that we talked about before, the 4 and the 9, it's dry mass. Okay? Because like if you throw in water, the density would be lower. Okay? So it's after you dry things up. Okay, I didn't mention it before. It's important to be clear about that. Now, with oils, they're usually without water, so that makes it easy. And for most of the cereals that we're eating, they also start as dry. Okay, like the rice, we talked about the rice before you added the water. Okay, so the bread, dry bread. Okay. So from this, we see that each one of us is eating about half a kilo per day. Okay, this was per day. So you divide this, about half a kilo per day. Which means that per year, it's about 200 kilograms per year. Okay, 365 days, I make it 400. So that's roughly the amount of kilograms I'm eating per year. Okay. How can that help me? Now I want to talk about like how much yield do I get in the field. So anybody here, comes from a background where they grew wheat or something? Something grew something? Okay. Okay. What anybody knows about whatever you grew, how much came out of it? Or let's say the following: if you pass next to a field where they grow wheat, okay, and you have the same meter square.
10%.
Okay, so remember what wheat looks like? Yeah, it's like this. And then you have something here. How much do you think the grains sitting on the top of the wheat, how much do they weigh per meter square?
100 grams?
Oh, meter square.
Half a meter square.
Half a kilo.
1
Yeah.
kilo, yeah, half a kilo.
Okay, so I didn't bring water today. So the question is like, okay, a great example. Everybody loves this, right? Awala or wala. So think about the meter square, and you have like this. How much of these can you put there?
100? 10?
No, I mean this is super heavy. So anyway, so maybe my intuition with this doesn't help. Forget it. Okay, so I heard 100 gram and I heard the kilo. So okay, somewhere roughly along those lines. So we had 100 grams to 1 kilogram per meter square of wheat. Okay, so let's continue for a second. We had 200 kilograms per year, and it's coming from, it needs to come from 2,000 meters square. Right? So from that, we could calculate the average yield 200 kilograms per year from 2,000 meters squared. It's not per
year per person.
Yeah. Anyway, we could solve that in a minute. So this gives me about 0.1 kilogram per meter squared. Or actually, the units that people like to work with in terms of yield in agriculture, you know what area units are used? Not meters squared, but... So they're using something called hectares. Okay, 1 hectare is... Just a second.
Like 100 meters per 100 meters.
Yeah, so it's 10,000 meters squared. Okay, and I want to work in tons, not kilograms. So 1 kilogram, 10 to the minus 3 ton. And, okay, that's 10 to the minus 4, that's 10 to the 4. So altogether I have 1 ton per hectare. Okay, so I just I converted from this, what we're eating and that area. I'm supposed to get a yield of 1 ton per hectare. And anybody, when they grew things, do you know how much they got from that field? So really, if you go and you try to search, statistics of what is being grown, let's say wheat, you actually go, this intuition was about right. It's a few tons per hectare per year. And this few tons per hectare is really few hundred grams per meter square. And this is for dry matter. It's actually true kind of across the board. My family has an orchard, it grows oranges. In terms of dry mass, it's also few tons per hectare. Okay, in terms of wet mass, you usually get much more because 90% is water, so it's say tenfold more. But this works well for rice and for potatoes and for all of those things. Okay, so this is the usual yield. This is what we just calculated with that efficiency, with this area that led to that efficiency. So I would say the difference is actually not that huge. It's a factor of a few. So first of all, in terms of the sanity check, it passed the sanity check because I didn't get like a different order of magnitude. I got something that's within a factor of a few. But you could also talk about, okay, but still this is a few times more than this. So what gets into this difference? What? Okay, so there's the fact that we eat more than 2,000 kilocalories. That's one thing.
The efficiency of the food system.
And waste of food.
Okay, so the efficiency in terms of waste. So there's lots of waste at home, in the supermarket, in the processing. There's the fact that was mentioned before that we don't eat everything that came out of there. And there's also effects of, some of the things, we don't get into this so much, but, some of that also goes into this thing that was mentioned before of going to animals beyond the pasture. That's also a major factor. So all of those things explain, this difference and why maybe you've seen efficiencies that are somewhat higher. That's because there's something about the efficiency that happened in the field. Usually it could be, say, up to an order of magnitude more. But in terms of converting it to what's human edible, you're losing along the way. So this balances those two things. But in general, I would say very low efficiency. But at the same time, we found a way to do a sanity check, to learn about how much area we need, what's the efficiency of what we do, how much food to actually you can get from that, the yields that you get in agriculture. So lots of good things come from just a few components that you know about. Actually, everything came from these 2,000 kilocalories that we eat and knowing something about the density. And from that, boom, you can derive so many different things. Which if you don't like that, you're in the wrong course. But if you do like, I think it's, it gives you a much more capability to do lots and lots of things. Okay, so in that spirit, I want to leave you with just one more thing to think about. And this relates to something I've heard and I didn't believe. And this thing that I've heard is the statement that in the coming 4 decades, humanity will need to produce as much food as it did since the invention of agriculture. What do you think?
I think we can calculate it.
I'm in favor of calculating it. I'm actually, is there a comment on how we did it, or it's good? Okay, actually, I'm so in favor of us calculating it that we gave it to you in the exercise to calculate it. So I think for now you can just reflect on this, try to think how would you try to calculate it. So let's take 5 minutes. So again, each one either by yourself or in pairs. Try to consider how would you try to calculate it. Because I'm not sure that at home you would resist the temptation to have ChatGPT calculate it. So try to first of all see how would you try to approach that. Okay, guys. So just before we go out, to give you time to do the other things you like to do in life and to solve the exercise, I'll just clarify one thing about this. In this case, I'm not trying to do a very accurate calculation I'm trying to see if this statement is just, clearly wrong, or it passes a sanity check. Okay, so in doing a sanity check, because, for example, you might ask, I don't know, 100 years ago, 1,000 years ago, did they eat as many calories as we eat today? I don't know. Probably they didn't. But the question is, I don't want to get into the fact that, maybe now we eat 2,000 or 2,500 and then they ate 1,500 or 1,800. It's not what I'm after. I'm not looking for these effects of, say, within like a factor of 2 or something like that. Because in any case, nobody would know the exact answer. We just want to see whether it's in the right order of magnitude. Okay, so in that spirit, try to approach it. Forget about, second order effects that, adds a bit, takes off a bit. We just want to see some way to get at an answer that would give you the order of magnitude. Okay, so in that spirit, I wish you good meals, good week. We'll meet next week. And success in the exercise.